NASA and its partners will be working to support development of minimum operational performance standards, or MOPS, for detect and avoid for medium-sized UASs utilizing small, lightweight, and low-power sensors.
From our side, we're pushing the boundaries for this small aircraft. We're trying to fly a radar that's small, tiny, and trying to pick up aircraft, and they're trying to define what that is. Again, it's a brand new radar, state-of-the-art systems. They don't really exist out there. Low swap systems don't really exist for aircraft. When you're dealing with smaller aircraft, a lot of it's hobby grade type of systems, avionics. A lot of it's not conducted to flying real aircraft. But now that we're actually trying to fly in the national airspace, we need to put real avionics on there, things that are tested to FAA certification. And that's pushing the boundary. I think that's what we're doing here with this low swap system.
So how is the NASA team pushing the boundaries? By using a number of unique control centers, piloted aircraft, and a UAS with a large number of flight hours to supply the needed information for integration. FT6 is a multi-dimensional test with many different groups of researchers and pilots working together to make sure the test goes according to plan. During each flight, there are several different researchers in different control rooms monitoring the flight, and there are also at least 3 layers of pilots in the air and on the ground. To better understand this complex dance, let's first look at the UAS that is being used. For this round of testing, NASA decided to use the Navmar Applied Sciences Tiger Shark XP UAS. This is a medium-sized aircraft with a wingspan of nearly 22 feet and can stay aloft for 12 hours. It's controlled remotely using a ground-based cockpit and has been equipped with a smoke-generating system to assist the intruder pilot with visibility and an early developmental low-swap nose-mounted radar built by Honeywell that will use a fixed-phase array to steer the radar beam electronically.
The Tiger Shark is a Group 3 unmanned aerial vehicle, 500-pound weight class, and it has been used as basically an R&D platform to enable NASA and NASA's partners to test various pieces of software and hardware to help develop standard operating procedures for integrating UAS into the national airspace relative to detect and avoid technology component.
Because this UAS platform has such a long and stable track record, the FT6 team felt that its reliability would allow them to focus their expertise on testing rather than worrying about building their own UAS. One of the most intriguing aspects of this test is the different roles and assignments performed by the team flying the UAS. The Navmar team pilots the aircraft during the initial takeoff and landing phase, but after the craft is airborne, control of the UAS is handed off to NASA pilots. The subject pilots that take over the flight are not aware of when intrusions into the airspace would occur, making it realistic to what pilots in the NAS would experience.
Open Center NASA 01, deviating for traffic 170. Open Center NASA 01, clear of conflict heading 030.
They must be able to react quickly without anticipating a solution to a scenario before the encounter has even occurred.
This is a subject pilot station, so what they're observing is the on-ship aircraft, and then they'll see intruder aircraft. The aircraft are generated by either virtually from Ames, and that's just to add background traffic to kind of create a real airspace system. And then you have real traffic that's picked up by the aircraft systems, and that's injected through the payload, and it comes into the system too. So they're getting a mix of both real traffic and virtual traffic. And all they're doing is essentially flying this mission. They'll get intruders coming in and causing traffic alerts. If it's a yellow alert, they'll either talk to ATC and move, or if it's a red alert, they'll move immediately, then talk to ATC and coordinate on their way back. This all done in Oakland airspace in a virtual environment from their side, even though they're flying the real aircraft with real intruders.
We were actually able to gather a lot of the metrics that you would normally gather in a lab, but in this case, a real atmospheric flight. And that's what we call live, virtual, and constructive. We had the live component, which is the live UAS and the live intruder. The constructive, which were traffic, simulated aircraft that were moving in the airspace. And then virtual, which were actually people who were flying simulated aircraft and talking over the radio. And all those things combined to create a really immersive test environment.
So this is the Mobile Operations Facility 5, MOF 5. So this is the NASA Ground Control Station. That's where we execute all the flight testing, all the missions conducted from this. So this system's interface to the Navmar ground station. It's interfaced to the LVC environment, and it's interfaced to the comm system here at Armstrong. So it, again, interfaces to all the systems and allows us to communicate with everything. So from here, once the aircraft's airborne, our pilots take control of the aircraft, move it into the airspace, and then after that, control is transferred to the subject pilot that's on this side of the station. And this is where we conduct the mission, the full mission for the flight test. So the subject pilot is not familiar with the system, and that's done on purpose. It's a human factors research. We need trained pilots to actually monitor the airspace and make sure that we're still flying in real airspace. And an actual Edwards Air Force Base, there's actually other missions going on in the background. So we need our pilot test to manage that part of the test and call it off if they need to, or take control of the aircraft if there's an actual emergency up in the air, or if there's another mission that's intruding.
These piloted aircraft are not only employed as chase planes, but are used to intrude in the airspace around the UAS to test the detect and avoid system. During these flights, intruder aircraft intentionally fly very close passing encounters to the UAS, which trigger the DAA alerting and guidance. These encounters test the detect and avoid procedures, helping researchers develop performance standards to address such scenarios. A typical test day starts off in the early morning hours. The team starts with a T0 briefing. During this time, all team members go over all the test parameters for the day. Once that briefing is complete, everyone goes to their respective locations, such as control rooms or to the aircraft. When everyone is ready, there is a comm check over a specific frequency. Meanwhile, the Tiger Shark is towed out to the lake bed for launch, while the intruder aircraft are preparing for takeoff. Once on the lake bed, a series of tests are performed on the aircraft to ensure it is safe and ready to fly. When all these tests are complete, the ready call is given, and the aircraft is set for takeoff.
And we have good RPMs, good systems, brakes off.
On this cold, clear morning, the aircraft takes flight without a problem to begin the day's test. Once airborne, the Navmar team hands over control to the test pilots to fly the mission for the day.
Put, this is AVP on mission, ready for handover.
Putt ready for handover.
Your aircraft, just a reminder.
Putt has the aircraft, Wilco.
In the various control rooms, teams of researchers are monitoring the system, while intruder aircraft begin the incursions into the UAS airspace.
Tiger 50310 heading as approved.
Right turn 320, 335.
On this day, each pilot sees the incursions and properly guides the aircraft away from the intruders.
Correction, right turn 350.
This test continued for several hours, with numerous intrusions occurring. As the test winds down, flight control is given back to the Navmar team, who then brings the Tiger Shark back for a perfect landing.
I've seen a trend so far working in the industry, and it's only continues to climb. When I first started, quadcopters or large UAS weren't really a thing, and now we've flown a large UAS in the national airspace for the first time, and now we're working towards integrating smaller class UAS into the national airspace as well. Eventually, everybody wants to jump in a taxi and have it airlift you from building to building. This technology, this detect and avoid technology, will really help that and conduct it safely.
Over the course of this comprehensive testing, NASA and the FAA have amassed an enormous amount of data, allowing safe, efficient integration of these systems into the national airspace. This type of result is not unusual for NASA and its partners. Over the past 60 years, this organization has continued to push the boundaries in science, engineering, and technology. While the presence of drones and unmanned aircraft begins to populate the skies, NASA will continue to test, evaluate, and pursue a safe and efficient airspace that will coexist with commercial and private aircraft. What many thought was science fiction will soon become science fact as these aircraft become a part of our everyday lives.
The bug for space really bit me when I came down to visit my grandpa down here in Houston. So I saw the big old Saturn V rocket sitting on its belly out there and just thought, man, if humanity can do something this amazing, this awesome, I want to be a part of it. And I just fell more in love with the idea of space and being a part of something bigger than myself. The thought of actually getting to space, I couldn't wrap my head around that. You walk up to this rocket that's covered in frost from the cold fuel inside, and it's creaking and groaning and kind of alive, and you're like, well, that's pretty cool, but they're probably going to cancel. It's just not going to happen. You know, I've done so many sims, and it just can't be real. There's no way I'm going to go to space. But then when no kidding, it lights off, and you feel the rumble, and then you start to move, and that kind of just constant, smooth acceleration, pulling you back in the seat. Everything comes to life on the panels. You see all of the things that you've seen 100 times in sims. In one instant, all of that I felt was unimaginable became real. And it was a magical thing I'll just never forget. You know, we're scientists and engineers and pilots and doctors. We're not poets, but we sure try to be, because you want to share as best you can the experience that you've seen and felt. I think I told my wife once I got on board that I thought it was
It's a burrito of awesomeness smothered in awesome sauce, baby. It's so beautiful.
It was just the beauty of being there yourself with your own eyes and seeing it. One thing that I would love to do while on orbit was, there was a window in one of the Russian modules that looked kind of out the back of the station. And I'd go sit there. I'd turn off everything, and you could get it really dark in there, let my eyes adjust, and just look out at the stars. And the stars, you know, the longer you sit, the more you see, and it becomes unbelievable. The number, the just billions of stars, the Magellanic Clouds, the galaxies that you can see with your naked eye. And they don't twinkle. They just stare at you. They dare you to come and to explore. It lights a fire inside your soul that is unlike anything I ever experienced before or since. And it's why you see astronauts, you know, they say 560, 580, I don't know how many people have gone to space. They're all the same. They all have that bug. And they all want to do everything in their power after experiencing that to make sure that humanity reaches its potential, that we get there, that we don't just see the stars, that we explore them, that we live there, that we grow into what we can be. And you're reminded of the incredible potential that we have as humans when we put everything else aside and just work together. And you feel a part of that, looking out the cupola and just being a part of thousands of people from across this globe that have put together this just palace in the sky for us to discover and learn and grow. It showed me the potential of what humanity can be when you work together as one team. It inspired me to do everything I can in my power for the rest of my life to enable humanity to evolve, to get there, to those stars that were staring straight in my face and daring us to come get them. That is something that you can never quench. It's been a couple years since I flew, and that fire still burns just as strong today as it will when I die.
Milestones in human progress that mark recorded history. In my judgment, this nation's orbital pioneering in space is of such historic stature, representing as it does a vast advancement that will profoundly influence the progress of all mankind. It signals also a call for alertness to our national opportunities and responsibilities. It requires physical and moral stamina to equal the stresses of these times and a willingness to meet the dangers and the challenges of the future. John Glenn, throughout his life, has eloquently portrayed these great qualities and is an inspiration to all Americans. This film, in paying tribute to John Glenn, also pays tribute to the best in American life.
Concord, Ohio wasn't on many maps until February 20th, 1962. It came to fame in a single day with an American adventure that history will call the John Glenn story. Fashioned in the American image, this pleasant little city typifies a nation's ideal way of life. A man might make a good life here in the circle of family and friends. And a boy might let his imagination soar. He might explore the wonders of the wide world all about him, life's simple mysteries, with bright discovery daily opening doors to knowledge. He can look away to distant places, to exciting adventures, hidden only by the horizon and the future. Like this boy, like boys everywhere, young John Glenn dreamed of the future as he looked to faraway new frontiers. Why, he might even learn to fly. This town and these people, they knew John Glenn as a schoolboy, as a teenager, and as a neighbor. Like Mayor Taylor, they followed his career as he blazed a trail across the high sky.
I watched John Glenn grow up from a freckled face, red-headed lad into the man you all know today. John's youth and his life today are an example for all Americans to follow.
New Concord High. Like these youngsters, John attended school here. His principal and teacher was Harford Steele.
He was an excellent student, and he graduated with honors from our high school. I taught Johnny and hundreds of others that our democracy is a priceless heritage, and that we should preserve, protect, and if at all possible, make some contributions to it. He has made a significant contribution in his mission in space.
And this fine new school in New Concord, it's the John Glenn High School, with its first graduating class receiving diplomas. Young John helped his father about this shop when he wasn't in school, or acting as lifeguard in the summer at High Y Camp or at college. John went on to college at Muskingum, right in New Concord. The high regard of the college is expressed by its president, Dr. Glenn McConaughey.
John's conquest of space has captured the hearts and the imagination of all Americans. So have his superb qualities of leadership, moral and physical strength, and emotional stability.
John found time for athletics, winning 4 high school letters. Muskingum coach Ed Sherman recalls John Glenn's athletic record.
John played football right here on this field. He was captain of his high school team and played center for the college. He has proven the value of teamwork both as an athlete and later as an astronaut. Just like these boys, John took an active part in our physical fitness program. He proved that a good mind and a good body always go together.
Campus discussions are inspired by the first orbital flight of an American.
I think that John Glenn, by his flight, has given us an opportunity to see that while we have a chance to do something for our nation, too, maybe I'll even go somewhere sometime.
We have the same opportunities that he had. Glenn proved by his flight that there are still many frontiers to be explored and conquered.
And that just shows how very vital our education is if our future is to be go.
Glenn always had a strong spiritual side, as Dr. Charles Moorhead recalls.
John Glenn attended Sunday school and services at this church when he was a boy like Randy Bradley here.
Let's attend services for a moment at John Glenn's church. John and Annie were married at this church by Dr. Henry Evans.
They made a most handsome couple. John in his Marine uniform, Annie a beautiful, happy bride. They both recognized the importance of the spiritual things of life as well as the mental and physical.
The trial is also great for those who wait, as recalled by Annie's parents, Homer and Margaret Castor.
Johnny's orbital flight was a real test of courage for Annie, too.
She was a very brave girl.
Annie had complete faith in the space program, just as she had confidence in everything Johnny set out to do.
This house was home for John Glenn. John Glenn Sr. and Mrs. Clara Glenn are gratefully proud of their son's accomplishments.
John was fully prepared for his orbital flight, as were the other astronauts and the entire team.
In a way, John has been preparing all his life for his venture into space. As a small boy, his idea of a holiday was a visit to the airport. And when he grew up, it was no surprise to us when he decided to learn to fly.
Flight commanded young John's major interest. He had to learn to fly. World War II interrupted college. He received his first flying lessons from pilot Harry Clever.
This is John's flight record with my comment after his first flight, which was eager to learn, relaxed, alert, and good coordination. He certainly has retained these flight qualities right into outer space.
Training at Pensacola and Corpus Christi. Many aviators have won their wings here. Like these cadets, John went on to Corpus Christi, Texas to learn about airplanes and navigation, with time also for physical conditioning and sports, and for religious inspiration. Like these naval aviators, to win his wings. The Navy's thorough training prepared Lieutenant John Glenn for wartime action in the South Pacific. Flying 59 missions in Corsairs like these, he joined in blasting enemy targets. Until there was peace, and Glenn returned to Corpus Christi as advanced flying instructor until Korea. Major John Glenn came back to combat to fly 90 missions, to shoot down 3 MiGs. Following Korea, John Glenn came home to flight test the supersonic F-8U Crusader, to flash across the nation, California to New York, setting a supersonic speed record of 3 hours and 23 minutes, with experimental thrusts towards speed and altitude. The limitations of time and distance were being brushed aside as experimental planes like the X-15 launched from its Air Force mothership rocket to record-breaking altitudes and speeds. Unmanned experimental flights and orbits pressed onward until it was time for man to orbit, until the word was go. Chosen from many Americans who answered the president's call, these astronauts dedicated themselves to study, training, and physical conditioning. With Alan Shepard learning about weightlessness as it will be encountered in outer space, and Gus Grissom becoming acquainted with the stress of greatly increased gravity, as Wally Schirra masters manual spacecraft control. 3 years of engineering skill and scientific experimentation have gone into this historic Atlas launching. Its component parts have come from countless sources, devised and fabricated by many thousands of technicians in hundreds of United States cities. And this, the motive power, carefully raised to position on its gantry. This, the Atlas, with power to develop 360,000 pounds of thrust, with capability to swiftly lift the spacecraft and its passenger as high as 160 miles, to inject the spacecraft into orbit at 17,500 miles an hour. And now the word is go, as the spacecraft is lifted into its position atop the Atlas. This spacecraft, 6 feet across at its widest heat shield end, 10 feet tall, built to withstand heat shield temperatures of 3,000 degrees Fahrenheit as the wind rushes by at more than 15,000 miles an hour. As the astronaut prepares for space flight, for adventure into outer space. Mercury control waits and watches, with the Atlas standing ready to throb into life. Ready. Friendship 7 is ready. And so is John Glenn. At the gantry, elevators lift Glenn to the 11th level, the spacecraft level. Glenn takes his place in Friendship 7, looking towards the unknown. Ready. Mercury Atlas is ready, and so is the astronaut. The countdown is underway at Cape Canaveral, as all the world holds its breath, and all the world is witness.
Godspeed, John Glenn. 5, 4, 3, 2, 1.
go, and with him go all of mankind's dreams of someday touching the unattainable stars. Under a tropic sun, the tracking ship Rosenaught waits and follows his course as he flashes towards the coast of Africa. To John Glenn belongs an awesome panorama of the Earth below. Beyond human sight, Friendship 7 makes a slow boat out of the sun as the spacecraft girdles the Earth every 90 minutes. Like a shooting star at 5 miles a second, 17,500 miles an hour, John Glenn streaks away from today into the night of tomorrow, racing towards the dawn of yesterday. As Glenn sights the lights of Perth and Rockingham, as he flashes over Australia, across the Pacific, to contact waiting ground stations at Guaymas, Mexico. And California waits as Friendship 7 streaks home to the land of its origin. An unseen comet lining across the United States in 8 lightning minutes of flight. Completing 3 history-making circuits of the globe, John Glenn fires retro rockets to slow the spacecraft, to direct it back to Earth.
5, 4, 3, 2, 1, fire.
Roger. Retros are firing.
Yeah, baby.
Are they ever? It feels like I'm going back toward Hawaii.
Then the first ominous note, the first warning of possible disaster. A chilling signal flashes an indication that the capsule's heat shield may be loose. The astronaut might perish like an earthbound meteor in 3,000 degrees of re-entry heat without the heat shield. Strapped over it, the retro pack might hold it in place. Cape Canaveral makes the decision.
This is Tectchef Capcom Section 7. We are recommending that you leave the retro package on through the entire re-entry.
As all the world listens and stands still and helplessly hopes, Cape Control shows the way. Using fly-by-wire control for re-entry, John Glenn rides his craft through the vastness of space towards the curving globe beneath. As science in its amazing exactness selects the Caribbean from all the oceans of the Earth to receive Friendship 7 as it blazes into the Earth's atmosphere.
This is Friendship 7, a real fireball outside.
A fireball. The fiberglass surface of the heat shield is starting to oblate, to melt and vaporize as a glowing electrically charged wake streams back to block off communication as the Earth's atmosphere slows the capsule's descent.
Friendship 7. Stroke is out. Coming down on 10, snorkels are open. Main chute is on green. Chute is out in reef condition at 10,800 feet and beautiful chute. Chute looks good. Rate of descent has gone to about 4.2 feet per second. The chute looks very good. Hello, Mercury Recovery. This is Friendship 7. Do you receive? Friendship 7, this is Steelhead. Be advised, I have you visually. Roger. What is your estimate on recovery time? Over. Estimated pickup now at 20 minutes. Over. Landing bag is on green. Friendship 7 ready for impact. Almost down. Here we go. Friendship 7, this is Steelhead. Hold you in the water. What is your condition? Over. Roger. My condition okay. Does the capsule look like it's okay? Over. The capsule looks good from here. Over.
Home to Earth comes the Voyager. Transported now to the aircraft carrier Randolph. In 4 hours and 56 minutes, John Glenn has streaked through 3 days and 3 nights and over 81,000 miles. Never a journey so far. Never a traveler so welcomed by the world. brief a journey in time. So far the way, so long the hours for those who wait, as Annie Glenn has waited. As all the world has waited. To salute the Glens with Vice President Lyndon Johnson. As the President of the United States arrives at Cape Canaveral to be greeted with John and Annie Glenn by the cheers of thrilled lines of proud Americans. In ceremonies at Mercury Control Center, President John F. Kennedy presents the NASA Distinguished Service Medal to astronaut John Glenn. As Annie and Lynn and David Glenn proudly share applause with the other astronauts and with the world. As John's parents learn firsthand about Friendship 7. As does Marine Corps Commandant General David M. Shute and the President of the United States. And this rainy day in Washington is a happy day as the President and the astronaut arrive to drive through rain-washed, crowd-flooded streets to the White House for a reception as John and Annie Glenn with Vice President Lyndon Johnson greet distinguished guests, including astronaut Alan Shepard. Godspeed, John Glenn. Godspeed into the future, into even greater accomplishment, into the hearts of all Americans. Welcome to Washington. Welcome back to this planet. From the nation's capital to the towers of Manhattan to the ticker tape parade of New York, cheering crowds roar a mighty welcome, shared by all Americans, by free people everywhere. And across the land, the scene is the same, and the heart is the same, as John Glenn comes home to New Concord, Ohio. At the Capitol, there's an introduction by the Speaker of the House, the Honorable John McCormick.
Members of the Congress, it is a privilege, and I deem it a high honor, to present to you a brave and courageous American, a hero in World War II and in the Korean conflict, who recently, in a most notable manner, added glory and prestige to our country, the first United States astronaut to have achieved orbital flight, Lieutenant Colonel John Herschel Glenn, United States Marine Corps. Colonel Glenn.
Mr. Speaker, Mr. President, members of the Congress, I am only too aware of the tremendous honor that's being shown us at this joint meeting of the Congress today. This has been a great experience for all of us on the program and for all Americans, I guess, too. And I'm certainly glad to see that pride in our country and its accomplishments are not a thing of the past. I know I still get a real hard-to-define feeling down inside when the flag goes by, and I know all of you do too. The launch itself was conducted openly and with the news media representatives from around the world in attendance. This is certainly in sharp contrast with similar programs conducted elsewhere in the world and elevates the peaceful intent of our program. Today, I know that I seem to be standing alone on this great platform, just as I seem to be alone in the cockpit of the Friendship 7 spacecraft. but I'm not. There were with me then and with me now thousands of Americans and many hundreds of citizens of many countries around the world who contributed to this truly international undertaking voluntarily and in a spirit of cooperation and understanding. We are all proud to have been privileged to be part of this effort, to represent our country as we have. As our knowledge of this universe in which we live increases, may God grant us the wisdom and guidance to use it wisely. Thank you.
And crown thy good with brotherhood, from sea to shining sea. In the pattern of all our free American traditions, John Glenn's trailblazing venture into space has shown the way for human progress, for brotherhood around the world. His story speaks of people and places and industry, of the greatness that is America. It sings of the unselfish aims of a nation striving constantly for peace, directing all its power and persuasion toward the preservation of freedom. In its majesty and magnificence, this is the land. In all their historic greatness, these are the people. And the John Glenn story is their story. It throbs with a nation's restless energy. It soars with the adventurous spirit of Americans everywhere. Across this vast spread land, in all its towns and cities, on all its far-flung farms and ranches, deep in its reaches of forest and plains, of winding roads and rivers, majestic mountains and lakes and sea-lashed shores, people turned their eyes and hearts toward the high sky, sending their hopes and prayers, riding through space with John Glenn in Friendship 7, as all the world watched and hoped, with mankind's wonderment about the universe, finding an approach at last toward fulfillment. In the John Glenn story.
Greenland, a massive ice-covered island in the northern Arctic, a land of pristine waters, enormous glaciers, and ancient geology, and for some, the site of a hotly contested claim of the oldest signs of microbial life on Earth. Meet Dr. Abigail Allwood, astrobiologist at the NASA Jet Propulsion Laboratory. Dr. Allwood is here in Greenland to investigate recently published findings of possible stromatolites, or microbial fossils, dating back to 3.7 billion years ago.
It's always when I go and see some rocks and outcrops in the flesh, that it's so much more eye-opening and informative than it is to read about them in papers. And absolutely the case with this one. When I came to see them after that paper was published, I very much doubted that interpretation, and I thought, well, we need to do two things. One, we need to put a paper out, and secondly, we need to do a workshop and bring a lot of people out here to also see what their opinion is, reach some sort of a consensus on what the right interpretation was.
Extraordinary claims require extraordinary evidence, and a finding like this requires further investigation. Dr. Allwood has gathered a team of astrobiologists and will now travel by helicopter into the wilderness of the Ishua Greenstone Belt.
So we're out here to study an outcrop that there is some controversy over. There is a group of authors that has made a claim that there are biosignatures in the form of stromatolites in these rocks. And there's another group of authors, I happen to be one of that other group of authors, that has refuted that claim. So we're out here in Greenland to study those outcrops in more detail and to try to get a sense of the geology that surrounds those potentially stromatolite-bearing outcrops and try to get a sense for what the ancient environment looked like at the time that those rocks were forming. The claim was such a big deal because if it proves to be true, then this pushes back the earliest signs of life in Earth's geological record by a couple of 100 million years.
It means that the window of opportunity for life to emerge doesn't have to be very big. You know, literally, as the last bombardment is occurring, that you can say that life can take hold. At least our one example that we have that life took hold. Go to Mars. It means that it only also had to maintain its conditions, its sort of cradle of life, its opportunity for life to emerge for that short period of time. It didn't have to sort of maintain it for a couple of 100 million years longer.
And when you go back to those very old rocks, they're usually altered and deformed, and it's very difficult to find those signs of life. But those are also the most interesting rocks to look at because we don't know when life originated on Earth, and we don't know what that earliest life was like. So the record that we have from geology is in these rocks that are very difficult to interpret.
Sorting out which way I'm going to put it.
Okay. Sampling here in Greenland is, it's not all that different from sampling anywhere else. A geologist's tools are kind of the same no matter where you go. You need a hammer, a chisel, a little, hand lens to look at the rocks up close, field notebook, camera, and you record your observations, and when you think you've zeroed in on a piece of rock that might be worth taking back to the lab, you get your trusty rock hammer out and just start banging away until the sample comes out.
When we're looking at rocks, trying to understand if they preserve evidence of life, we look for things in the rock that cannot form without the influence of life. They can change the chemistry, and they can actually change the shape of the ground. And they can make things like peaks and domes that are sometimes unique to the biology.
Again, I think here what you need to do is look at the context of the rocks around those stromatolites and try to get a sense for what that geology is telling you.
This is our sample here. Came from the outcrop. We've got that new sort of cut and polished face there. And if it was really a cone-shaped structure, then you shouldn't see it on the back of the sample. You shouldn't see it in the back of the hole there. That's about 14 centimetres depth hole, and you're still seeing the structure there. So it's not a cone, it's a ridge. If you can sort of reconstruct that in your mind. Got to prove the three-dimensional morphology. Absolutely have to prove. It's the same story. You can see the structure at the back of the hole there. It's maybe 15 centimetres or so. It was present at the front and it's present at the back, so it's at least that distance in length. It's not a cone shape at all.
A lot of times when you're looking for something that's related to Earth history, I think of it as being like I'm a detective and I'm looking for clues. But the thing is that the rocks are not very good at preserving clues. And my job as a geologist is to take those little bits of information and see if I can make a story about what happened in the rocks. Part of making that story, though, is understanding the uncertainty. The story is never complete because you're always missing a lot of the clues because the clues have just been lost through time.
After investigating the site thoroughly, the team concludes that there is insufficient evidence of life in these structures. However, there is still much to learn from the geology in this environment.
The rocks that we're looking at here in Greenland are similar, if not identical, in age to the rocks that we're going to be exploring with the Mars 2020 rover. We'd like to think that we can use the lessons that we take from studying the Earth's geological record and apply them when we start exploring the geology of Mars.
One of the really interesting things about searching for life on other worlds is, as a scientist, I have to actually, when I'm looking for life anywhere, I have to actually have a model of what I'm looking for to help guide my observations. And so by looking at these places that are very difficult to interpret on Earth, we get that practice and experience of how do we look at something and what are the questions that we need to ask and what are the observations we need to take to be able to answer them.
Any claim that is made about a biosignature on Mars is going to be debated. So I think that this workshop gives us an opportunity to exercise our ability to have civil disagreements over matters of scientific importance, because I think we're going to be doing much of that with the data that comes back from Mars as well.
I think seeing the rocks in the flesh is just so important. Can't do that for many people, so I think the next best thing is to try and recreate that in a virtual terrain sort of field trip kind of thing. That's what we're trying to do.
So OnSite is an application that we developed for the Mars Science Laboratory mission to help the science team that works with the Mars rover understand the context of the environment around the rover.
And it provides scientists the ability to basically meet on Mars. So it's taking Martian data down from the rover and using photogrammetry to stitch it together to create a 3D model of the outcrop. And then scientists involved in the mission and engineers as well are able to use that 3D model, enter the terrain and make decisions with a much better understanding of the context. We're also using LiDAR imagery out here, which is something not available on Mars. So that's using a laser scanner to basically three-dimensionally scan outcrops and get higher fidelity data so that we can get some very accurate information.
Yeah, so this is the map of the primary outcrops and the laser scans. This is the A outcrop here. There's the flag, there's the cut of the rock, and the other cuts. Now on Mars, it's a different scenario because we're limited to the instruments on board the rover. The rover doesn't have LiDAR. It'd be great if it did. So all we have are the 2D images to work with. 3D reconstruction from 2D images has been part of the Mars missions all the way back to Pathfinder in the late 90s. But it's always been on a per image basis from one rover position. So one of the innovations in OnSite is we started combining rover imagery from multiple rover positions. So if the rover is parked next to a rock and the next day you drive around the rock, you can take imagery from those two positions and get a more complete model of that rock than from any one position on its own. And the holy grail of this is to take all of the rover drives from landing to the current position, register them all together so you could walk from the landing site to the current rover position, seeing high quality 3D imagery all the way. So OnSite was started in the context of the Mars rover missions, but the capability that OnSite and tools like it provide is really, it's a virtual presence and situational awareness in an environment that's hard to visit. Mars is an extreme example of that, but where we are today in Western Greenland is not quite as hard to visit as Mars, but it's certainly not easy. So you can imagine geologists going into the field to these remote locations and bringing back not only their written field notes and photos, but a 3D capture of the environment that becomes kind of an immersive field notebook that they can revisit, they can share with their colleagues and with the public and help to communicate what that environment is like in a way that's really hard to get without actually being there in the field.
So I don't think this technology ever really replaces a human in the field. Whether or not humans will go to Mars is not my expertise. But if and when humans do go to Mars, only a select few will go to Mars. But with this kind of technology, they can bring along experts from Earth to extend their knowledge and share that experience with the public, so the whole world gets to go along, for the ride.
So I've never been here before, and the landscape in this environment is just, my mind has been blown being out here for a couple of days. I mean, the scale of the glaciers, the complete lack of vegetation in this area, other than sort of, lichens and moss, it's kind of an otherworldly place. It's really starkly beautiful. I think in terms of why anybody should care about these rocks, I mean, they are the record of some of the oldest processes occurring on our planet. I mean, there are very few places that preserve rocks this old, and so they're really a precious resource for geologists to understand what was going on the Earth, close to, in its infancy. So it's an important and special place.
I will gain a huge insight into these particular rocks, but it will also increase my understanding of how you actually demonstrate that something is or isn't a biosignature that I will apply in all my other work.
It's the ability to minimize the ambiguity before it even gets to the publication, minimize the ambiguity and minimize the bias. When it gets out into the press, it's going to be that much more considered, that much more robust. I think that's what's the best outcome of this workshop.
In 1988, Dr. James Hansen, then director of NASA's Goddard Institute for Space Studies, stood before the U.S. Senate and testified that
global warming has reached a level such that we can ascribe with a high degree of confidence a cause and effect relationship between the greenhouse effect and observed warming. It is already happening now. This last year, 2021, comes in as the 6th warmest year on record, and it continues this large, long-term warming that Jim Hansen was detecting even in 1988. And in 1988, that was also a globally warmest year, but now that ranks only 28th in the ranking. And so the warming that we've had since Jim Hansen's testimony has been dramatic and totally vindicates the concern and the warnings that he put out at that time.
The Goddard Institute for Space Studies, or GISS for short, maintains NASA's record of Earth's surface temperature, called GISS temp, that shows a clear and unequivocal increase in our planet's temperature. GISS temp stretches from 1880, long before NASA existed, until the present day. Now, when you think of NASA, you probably think of, well, space, right? And we do lots of work studying Earth from above. But the GISS temp record is actually built from the ground up. We collect measurements taken from weather stations, Antarctic research stations, and ships and ocean buoys all around the planet to understand what temperature changes look like globally. And why does the record start in 1880? That's the earliest period that we have sufficiently reliable measurements from ships and weather stations in enough places to be confident in the global record. Interestingly, it's also shortly after the time we call the Industrial Revolution, when humans started putting significant amounts of carbon dioxide in the atmosphere. But we'll get back to that later.
There are millions of measurements over the last 140 odd years. We put those together. We're using data from literally tens of thousands of different stations around the world. We use the information that's there to create a global picture of what's happening. And that gives us a very accurate estimate of how any year ranks, or what the anomaly is for any one year compared to what happened in the 19th century or what happened in the middle of the 20th century.
So we have our statistical reconstruction of Earth's recent climate, but in research science, we like to check our work. There are a couple ways we can do this. First of all, teamwork. Our colleagues at NOAA and at other agencies and universities around the world also create their own records, and we can line them up side by side and see just how closely they align. Everyone's independent climate records show the same thing. Earth is warming significantly and rapidly. And here at NASA, we have an even cooler way to check our work: space. Right now, we have more than 24 satellites dedicated just to studying our planet. Satellites can take measurements of the entire planet and line them up with our estimate of global temperature change. And sure enough, they also match. Our measurements from space match up well with what our analysis tells us. Earth's climate is warming. The next big question: why is our planet warming? Well, let's jump back to the Industrial Revolution. The release of carbon, mostly carbon dioxide, from human activities like driving cars, flying planes, and industrial burning of fossil fuels is responsible for the majority of climate change. Carbon exists in stores underground as oil, gas, and coal. When we burn it, we release it into our atmosphere, where it traps excess heat coming from the sun, raising the temperature. We've known for more than a century that carbon dioxide added to our atmosphere traps additional heat and is a major contributor to the greenhouse effect. So we can also track the concentration of carbon dioxide in our atmosphere, the primary cause of the current climate change. Both from space, using NASA satellites like the orbiting Carbon Observatories 2 and 3, and from the ground. If you've heard of the Keeling curve, you're familiar with one of these records. Researchers have been taking daily measurements of atmospheric carbon dioxide from Mauna Loa, Hawaii since the 1950s. From space and the ground, the signal is clear. There's a lot more carbon in the atmosphere than there used to be. Other things have changed too. We've chopped down tropical forests, caused the ozone hole, and filled the air with soot, smog, and other kinds of air pollution. And this is on top of natural variations caused by the dynamics of the ocean, or volcanoes, or variations in the sun's activity. And so we can ask whether it's human activities warming our planet. At NASA, we have some big and powerful computers, able to make 6.8 trillion calculations per second. We put these huge supercomputers to work to recreate Earth's climate. So we have thousands of ideas of what could naturally cause climate change. We have 4 billion years of history where nearly anything and everything you could imagine has impacted Earth's climate. But each of these events has their own distinct fingerprint, which we can identify, a pattern of behavior with natural variability. Using supercomputers, we can run simulations of natural climate drivers, solar energy changes, wobbles in Earth's orbits, ocean turnover, volcanic eruptions, and we can run simulations of human effects. And what we've seen is...
it's us. There's no way around it. Looking at the evidence, we're the force that's enacting these changes. I am so proud of our ability to understand the climate, but I'm terrified of what we found.
But it's not just the causes of climate change, it's also the effects. Because it's not just about knowing why our planet is warming. It's also about understanding and preparing for the effects of added warmth.
Measurement of global average temperatures is so important because it's one of the most direct indicators of Earth's changing climate. But the Earth is really a system of environmental systems: land, ocean, atmosphere, and ice, and changes in one system impact the others. Our oceans are our first line of defense in climate change because they absorb so much of the extra trapped energy in the Earth system.
We are seeing the impacts of climate change now. Now we know that as our climate warms, wet areas are getting wetter and dry areas are getting drier. For example, we see more intense snowstorms. We see slower hurricanes that are causing more precipitation that inundate land. And we have more extreme precipitation in the form of atmospheric rivers that come from the Pacific and reach our west coast.
The oceans are absorbing a large amount of heat because of climate change. And once that heat is in the ocean, it actually travels all around the planet because of the ocean currents. And that has impacts on local weather and long-term climate.
As the planet warms, it's not just the ocean that's warming, it's also the ice that sits in the ocean and on land. The ice on land being warmed increases melting, which is increasing freshwater input into the polar oceans and causing sea levels to rise across the globe.
So as the climate is changing, we really are seeing a lot of changes to the environment up in the Arctic. We're seeing more permafrost thaw when it's warmer up there. The warmer air temperature can lead to warmer ground temperature, and we get that thawing of that permafrost layer.
We're finding that the fire season is being exacerbated by longer periods of drought and decreased snowfall.
Knowing that our climate is changing due to human activities means that we know how to lessen the effects of future warming. And knowing how we know what causes climate change confirms that our efforts would be meaningful. The situation is serious, but it's not hopeless. Together, we can decide to make a better choice.
A commercial mission returning cargo from the space station, the first space station spacewalk of the year, and observing a massive volcanic eruption from space. A few of the stories to tell you about this week at NASA. A SpaceX Dragon cargo resupply spacecraft is slated to return to Earth from the International Space Station loaded with more than 4,900 pounds of cargo, including supplies and an array of microgravity scientific experiments. The Dragon's return will cap off SpaceX's 24th commercial resupply services mission for NASA. On January 19th, 2 Russian cosmonauts ventured outside the International Space Station to conduct the station's first spacewalk of the year. During the outing, Anton Shkaplerov and Pyotr Dubrov of Roscosmos performed work to prepare the new pre-shell docking module for future Russian visiting spacecraft. The first docking to pre-shell is targeted for March, with the arrival of 3 cosmonauts aboard a Soyuz spacecraft. Several Earth-observing satellites are helping scientists affiliated with NASA's Disasters Program collect and share data from the massive volcanic eruption that obliterated the small uninhabited South Pacific island known as Hunga Tonga Hunga Ha'apai. Damage assessments are ongoing, but preliminary reports indicate that populated communities in the island nation of Tonga have taken heavy damage from volcanic ash and a tsunami caused by the eruption. Engineers at our Stennis Space Center conducted the first RS-25 engine hot fire test of the new year on January 19th. 4 RS-25s will help power our Space Launch System, or SLS, rocket on future deep space missions, including this year's uncrewed Artemis 1 mission around the Moon. This was the second overall test in the current test series, which began in mid-December. Each test provides valuable data that can be used to help develop the engines. The team assembling our X-59 quiet supersonic technology aircraft is making great progress with the developmental X-plane. The crew successfully added the tail, attached and tested out the positioning of the nose, performed a system check of the ejection seat, and moved the X-59's GEF-414 engine to facilitate a 3D engine scan. This scan helps engineers better understand the F-414's fit in the engine bay. The X-59 is being built to conduct research aimed at reducing the loudness of sonic booms that can occur during supersonic flight. That's what's up this week at NASA. For more on these and other stories, follow us on the web at nasa.gov/twan.
I call it the 10% rule. You got to be 10% smarter than the thing you're trying to operate. My name is Greg Cormouche, and I'm here to test rockets. We supply helium, air, nitrogen, and hydrogen so that they can use them while they're testing the rocket engines on the big stands. We have 4 compressors. Each compressor puts out 400 standard cubic feet per minute, and we send that to the test site. I'm a mechanical engineer. I did a lot of mechanical things besides go to college. I mean, I worked on my own cars, heating and air conditioning work. I was familiar with electricity. The first time I walked out on the engine deck and looked at a space shuttle main engine, I said, man, it was overwhelming, you know. Eventually, you know, you stick to it, and I was able to pick it up. The folks that work here are awesome. There's a wonderful group of men and women who keep this place up and running. When you're here as much time as we are, this place is like family. Being a part of the SLS program it's a life event, you know. This is going to be the culmination of all that hard work that everybody put in years ago.
This is Houston. Are you ready for the event?
Station's ready.
The Courier, this is Mission Control Houston. Please call station for a voice check.
Station, this is Amy Rivers with the Courier. How do you hear me?
And Amy, I've got you loud and clear.
Great. Thanks for speaking with me this morning, Raja. I don't know if you were aware, but the mayor of Cedar Falls organized a watch party to witness you commanding the shuttle into space November 10th, which they found very awe-inspiring. So I'm sure they'd want to know, what was that like for you blasting off from Earth and traveling to the station?
Well, yeah, I know Mayor Green had emailed me that they were setting up something, so I appreciate the folks of Cedar Falls and Waterloo coming out to watch. Honestly, it was a lot like the simulator, which I think is a great testament to the training teams at NASA and Johnson Space Center, as well as SpaceX in our case for the Crew Dragon. But it really felt like we were sitting in what we call the Buck, which is the mock-up at SpaceX in Hawthorne, other than the fact that there was a whole lot more noise and the feeling of accelerating. It kind of felt like going up in an elevator. If you've ever gone to like a skyscraper and those elevators that go up really fast, that's sort of what it felt like early on. And then once the first stage cut off and the second stage lit, you get the feeling sort of like you're in a car, like decelerating really fast where the seatbelts lock out, and then accelerating really fast when the second stage lights. And then, of course, once the second stage went out and we were weightless, that was a pretty amazing feeling. It felt kind of like being in a roller coaster initially, like when your stomach drops, but it keeps feeling that way, and then it takes a little while to adjust. But it was pretty amazing experience. We were all cheering and giving each other high fives once the second engine's cut off, the second stage cut off.
What's living on the space station like? What's a typical day for you?
So that's one of the coolest part of the jobs, is every day it's completely different. There's kind of, in my mind, 3 sort of big things going on. One is research, obviously, and within that there's 2 things. There's human research, so where we're the subjects, and then there's what I call like basic science, fundamental research. And so in that case, we're the eyes, the ears, the hands, really, for scientists on the ground that are doing experiments. So that's the 2 biggest things. And then the other part is housekeeping and maintenance. And so the station's been manned, or people now for 20 years and continuing now through 2030 with the current budget plan. And so just like a 20 to 30-year-old house, there's plenty of tasks that have to be done to keep the lights on, keep the water running, keep the air workable in our case. And so I'd say a good chunk of our job too is all the maintenance and housekeeping that goes with that. And so on any typical day, they plan our weeks based on the priorities, but every week and every day is slightly different depending on what's going on. So the last about month, the Cargo Dragon has been here with a bunch of science, and Cargo Dragon is unique, and it's the one vehicle that goes back and lands. And so any science that takes the ground to analyze it, we try to pack into that time while it's here. So we've got another day before that goes back, but there's been a whole lot of science this last 3 weeks.
And before we get into the science, I wanted to just ask one more sort of housekeeping question. What's it like looking down on Earth for more than 200 miles up? Are there any interesting landmarks or weather patterns you've spotted?
Yeah, so I think the thing that's most striking is there's a whole lot of water, which I guess you academically, I knew that, more than 2/3 of the Earth is water, but when you see it out the window, and just about every time you go and look out the window, it's water. And then when there is land, it goes by pretty quickly compared to how long it takes to get over the oceans. And then the next most striking thing is it's really hard to figure out where you're at without cheating and using a map. And I think it's just a testament to the fact that there's really no borders or lines other than the ones we create. And so when you look at it, the Earth from space, it's just one homogeneous mass of different land masses and water, and it's pretty cool and enlightening, I think, to think of it that way, and also realizing the fragility of it. And I think that's the other striking thing. We see 16 sunrises and sunsets a day, and as the sun either rises or sets, it highlights, and basically what it does is illuminate just the sliver of atmosphere. And when you realize how thin that sliver is, you can actually see the upper edges of it as you look kind of edge onto the Earth. And it's, compared to the Earth, it's like the shell of an egg. It's so thin, and just realizing that's everything that we know and love and understand is in that one little thin shell. Just really striking how important it is to preserve that.
Sure. Of course, you're not up there to hang out and sightsee. You, as you noticed, are working on some pretty crucial research. I wanted to ask you first about the long-duration spaceflight experiments that you had mentioned when we talked previously. What have those entailed, and what are you finding out so far in the course of that research?
Yeah, so what we know about long-duration spaceflight is there's a lot of things that change in your body, both at the macro level and even at a microscopic level. And so Mark Vandehei, who's up here with me, he's on track to be up here for over 300, basically a year. And we've got Christina Cook, who was up here essentially a year, Scott Kelly. So we're building that data set of people who are here longer term to understand what happens as we go beyond 6 months, 7 months, and on to years, which we'd have to understand to go to Mars. So some of the things we already know that we are confident about is it has a lot of the similar effects like aging, like the equivalent of aging. And so whether that's your arteries hardening, whether it's bone loss, some eyesight changes, things like that, most of those go back to normal when you land. And there's also some DNA changes. So when Scott Kelly was up here, they had the benefit of doing a genetic study between him and his brother, and saw actually DNA changes while he was in orbit. And those were actually opposite those macro changes. So it was actually getting rid of some, or changing the DNA in a way that actually shortened, I guess, or had the reverse effect of aging. But when he came back, it reverted back to normal. So those are definitely things we're trying to understand more about. Some of the studies we're doing on our current mission are having to do a lot with the gut biome and trying to understand that with different foods, different diets, and then taking a look at how that is a predictor of some of these other things, which also has implications for Earth researchers. We look at how the biome in your gut can be an indicator for all kinds of other diseases or conditions.
And you had also previously mentioned combustion research, materials research. How many research projects are you undertaking while you're up there, and what's been some of the more memorable ones for you, or ones that you think might have the most interesting implications for life on Earth?
So, Amy, it's hard to listen. There's over 300 in the time we're up here, which is pretty amazing and also hard to keep track of. It's more than one a day going on. I think, and to your question, so the combustion thing, actually, just the other day, I was swapping out what's called the ACME experiment. There's an igniter and a very tiny sphere of an alloy that gets superheated. And so some of the things we're investigating with some of that combustion research is cold. We call it cold flames. And some of the benefit there is if we can find flames or combustion processes that have lower carbon emissions. And so, obviously car engines, any kind of power generation that involves carbon fuels gives off carbon emissions. And so if we can find ways to combust that at a cooler temperature and do it controllably, that would be game-changing for carbon emissions on the Earth. The other thing that we were working on as part of the space, that what SpaceX brought up, and that Cargo Dragon, was some genetic research on plants, and specifically some cotton plants. So cotton is really hard to genetically modify on the Earth, and so here we can do it a little faster and kind of come up with maybe some ideas as to making basically cotton more drought resistant. And so cotton is a pretty big product on the Earth, used in everything from clothes to manufacturing. And so if we can figure out ways to make that require less water, that would have big implications for farming across the world.
Mm-hmm. while you're up there, how often have you been able to call or send and receive messages with your family and friends? And what's that process like? Is it just like a regular phone call or sending an email? Is there a delay?
So it's pretty similar, especially with my immediate family. So I'm able to talk to them about once a week via video call. It's a lot kind of like a Skype or a FaceTime type format, and feels very much like that. The only difference is there's a little bit of a lag. So we were trying to, if we're trying to do real-time interaction, you have to wait a few seconds, and then that bandwidth that's required to do a video requires certain satellites, and so every few minutes there'll be like a handover when we change from one satellite to another, and so there'll be a break in the communication then. But the ground control team does a great job trying to find the biggest blocks of chunks of time so that we have a chance to talk to our families and catch up on things. And then for phones, it's essentially an internet phone, and so we can dial down. People can't call us, but we can call them. And again, though, it's dependent on the satellite tracking times and coverage time. So when we have a satellite that can basically point at us and point at the ground and relay that information, then we can use the internet phone and call down. But and then email, we are able to email, and we get those pretty regularly. We do actually still have keep track of what's going on the ground with our jobs and stuff there, and so they come through pretty quickly. There's just a size limit on attachments, but we're able to keep up with all the stuff going on in our office back home.
For better or for worse, I suppose. And when is your expected arrival home? And once you're back, how long until you find out if you're picked to go on the Artemis mission to the moon?
So right now we're slated to come back at the end of April. It really is dependent on Crew 4, which is the mission that replaces us. So that will be the next SpaceX Crew Dragon that comes up here to man the International Space Station. And what we'll have to do is what's called a direct handover, meaning they'll have to show up, and then once they show up, we'll take the time to kind of show them the ropes up here, and then we'll come back. And so right now that's slated for the end of April. And then as for Artemis, right now the goal is still by 2024 to be beyond, trying to put humans back on the moon to stay this time. And so there's a large group of us in the astronaut office all working different projects on the Artemis development. So there's the SLS, which is the rocket part, the heavy lift to get us out of low Earth orbit and into lunar and eventually Martian orbits. There's the Gateway, which is kind of the lunar space station, which is the place where we would go to and then use that as a base to go to the surface and then potentially on to Mars. And then there's the Orion capsule, which is the way to get from the rocket to the Gateway, and then finally the landing system, which is the way to get actually to the surface of the moon. So 4 big projects all going on simultaneously, so plenty of work and development going on, and lots of work, and everyone's really charging ahead. And so, yeah, when I get back, I will probably get involved, I imagine, with some of the development. There's a lot of testing going on, so everyone in our office has been helping out with that. And it remains to be seen how we figure out who winds up going on those missions. But with the plan of Artemis to go to the moon to stay, I think there's going to be lots of opportunities for decades to come, not just for me, but for all the kids in high school and college. We're going to the moon to stay, and Mars and beyond. And so there's definitely room for a lot of people to help out and be part of that.
And speaking of those kids that are watching you in this mission closely, what would you say were some interesting or weird things that have been going on that you weren't aware of before you actually got to space?
I think for me, it was weird, but also pretty amazing how quickly your brain adjusts to this. And so, for about the first 2 or 3 days, I mean, you kind of feel a little stuffed up. It's like I mentioned, when the second stage first cuts off, you feel like you're falling, and that sensation doesn't go away for a while, and eventually your brain has to make that the new reality. It's the one thing we really can't train for on the ground, so we can do just about everything else except actually work in near zero G. And so actually experiencing that and adapting to it, to me, has been the most surprising thing and the most amazing thing, because after about 2 weeks, your brain just sort of figures it all out. So early on, when I would come out of our crew quarters, there's kind of one back behind me here. So this is one where Matthias, my European crewmate, lives in. So we actually live, when we sleep, we're inside these. And for about the first week or so, when I would come out, I'd always have to orient myself right side up and try to figure out where everything's at. But over time, it became a lot easier just to work on the walls, on the ceilings. And now as we go between modules, there's really no sense of a right way to be up or down. You pretty much adapt as normal. And honestly, really the only time we do think about it is when we're talking to people on the camera, because it's really disorienting for people usually on video. If we're talking to them or flipping upside down, talking back to them, it's hard for them to track us. But other than that, it doesn't really matter which way is up, and it's pretty amazing how fast your brain can just learn from that. That's actually some of the research we're doing too, is some sensory perception research where we wear different things that eliminate either our sight or our hearing, and then try to look at how the brain adapts to that, which has implications on the Earth for people who've been in injuries or have disabilities and have different neural pathways depending on the senses they have.
And finally, any message that you want to send to the Cedar Valley now that you've been up there for a couple months?
Yeah, I love looking down in Smotin, Iowa. I've gotten better at it. My big landmark is to find Lake Michigan and then work my way west from Chicago, and I can always find the bump out around the Quad Cities and Dubuque area, and then work my way along I-35 and I-80 and kind of find all the major cities. So it's always comforting to be able to look down and spot my hometown, spot where I grew up. And yeah, I think my message would be, thanks to the teachers, the community, everyone that got me and my family here. My wife, as you probably know, is from Cedar Falls as well. And so I think both of us consider ourselves homegrown in Iowa and the Cedar Valley. And really the reason I'm here and the reason she's as successful as she has been is thanks to the support and love we've got in the Cedar Valley as kids and even as adults now. And so, yeah, thank you very much to all of you who helped enable us to be able to do this research and great work up here on the space station for you.
That's all the questions that I have. I really appreciate you talking to me today, Raja.
Yeah, no problem, Amy. Thanks for taking the time to do it, and appreciate it.
Station, this is Houston ACR. That concludes the event. Thank you.
Thank you to all participants from the Courier. Station, we are now resuming operational audio communications.
Testing 1, 2, 3. Testing 1, 2, 3.
Welcome to NASA Edge.
An inside and outside look.
At all things NASA, and in honor of the upcoming LCRD, Laser Communication Relay Demonstration Mission launch.
Hey, Blair, we can't hear you.
Deployed my own laser
Blair,
communication
we can't hear
system. Yeah, you got to use the earbuds. You got to be part of the game here. I've developed this system, and you guys will not only have audio, you'll have video, you'll have lots of terabytes, lots of data.
Hey, we still can't hear you.
Try harder. Like, listen.
This is not working.
It's nothing.
Everything says you're good. You should be good.
You need to workshop your thing.
What'd you say?
But no, we should be good. Just
Hey,
go
tell
with
you
the
what, here's
show.
what
Keep
we're
it
gonna do.
rolling.
We're going to go ahead and continue the show from here. You just work on whatever you're doing, and we'll get back to you. All right, bye. Hey, tell you what, on today's show, we're going to be talking about the Laser Communication Relay Demonstration Mission.
Or LCRD. And we have subject matter experts from NASA headquarters, the Goddard Space Flight Center, MIT. They're all going to come and talk to us about the evolution of space communication, and in particular, on this show, laser communication.
Well, before we get into the components of LCRD, let's focus on space communication first.
Using my system.
Jason, can you tell us a little bit about your role with space communication and navigation?
Sure. At SCAN, our job is to enable NASA missions. We enable exploration, we enable science by providing the mechanism by which you communicate to and get data from satellites, whether they're crewed or robotic. And we're responsible for making sure that they can navigate as well. Essentially, we move bits for the missions and we help them understand and know where they're at, how fast they're going, and what time it is. All very important pieces of information.
How will LCRD help NASA missions moving forward?
So LCRD will be our foray into relay in optical from geostationary orbit. Just like terrestrial bandwidth needs, everybody wants to have more bandwidth. We need more bandwidth to accomplish our mission. The thing that we will be learning from that is how to operate an optical relay from GEO. That will help with terrestrial optical needs, but that will also be a learning experience for us about what we would want to do in terms of high bandwidth data aggregation at the moon as we focus on sort of building up that exploration capability for sustainable lunar presence. One of the things that is a fundamental responsibility for SCAN is to enable exploration and science, and lessons learned from LCRD will help us do that in the context of essentially building an internet in space where the sustainable lunar presence will be the framework that will learn all those lessons. Because you want to try and reduce the burden on users, that they don't have to carry as much equipment, right? So you wouldn't want to carry a cell base station around all the time with you with your cell phone. You just want to carry your cell phone. So we want to make sure that the user burden at Lunar is low. We can aggregate that data and send it back over these high bandwidth data links. But then that extends exactly in a replicatable way to what we expect we will need for exploration at Mars. This is exactly the kind of thing that we need to have because the data rate for the things we will learn at Mars will demand high bandwidth. And we expect that the optical will serve that purpose for us.
Will this cut down on the transmission time of the data that we receive?
Unfortunately, we are subject to physics of light time. So we can't hurry it up, but we can get back more.
Jason Mitchell was exactly right. Bandwidth is key. But before we get any further, I just want to know, you guys, are you hearing everything? Are you getting the data through the laser communication system I've developed here? Everything on my end says go. We're good.
Are you talking about this contraption that's in front of us?
Be careful how you mess with that. It's very sensitive equipment. But yes, and it's working. Everything on my end says it's working. I think we're getting good data. And what I want to do for you guys is give you a demonstration and show you how much bandwidth I can actually send you via laser.
Tell them what we had to do.
Well, first we had to tinker with what you gave us to get it working. So now we can actually hear you, but whether or not we are going to receive gigabytes of data from
get
you
ready.
Remains to be seen.
You'll receive more data than you've watched on Netflix in the last 6 months.
No, before we get started, you're saying you're going to send gigabits of data through this contraption through LaserCom.
Right now. Get ready. I'm sending it. I'm highlighting. I'm sending it. This is it. Big time. And get ready for viewing. Did you receive it?
Nothing.
Not a
Did you?
thing.
Did you? It's there.
All right, Blair. We can't see anything right now, so while your data is in transit, we're going to carry on with the show.
You know, a big part of LCRD is the partnerships involved. And Jade Wang works at the Lincoln Labs at MIT, and she has a big part in this mission.
Yes.
Let's see what she has to say.
Okay.
Jade, I understand you work quite a bit with laser communication or optical communication. Can you tell us, what is laser communication?
Laser communication is using light to transfer information instead of using electrons. So in your computer, usually what happens is you use electrons to transfer bits, like ones and zeros. But with laser communications, we turn those ones and zeros from electronics to light. And so, for instance, you can transmit the same information by like turning on and off a laser pointer.
So how does that work in space? Because obviously we have a lot of infrastructure here on Earth for laser communication, but how do we do that from, say, the LCRD relay mission?
The difference is on the ground, it's being transmitted through these very small fibers. They're like small strands of glass, basically. And in space, what we do is we just beam the light out through free space using a telescope. So kind of like how you can use a telescope to like look at the moon, or if you want to look at where LCRD is, you can look at where LCRD is using a telescope. That's how you collect the light. You can also use a laser pointer and a telescope to transmit light in the same way. And so they'll just propagate over space and through the atmosphere and carry information in exactly the same way.
Now, that's obviously very impressive, but it seems like there's a big challenge when you think of sending information that way, because it's very direct as opposed to radio signals that are kind of broad.
Yeah, that's correct. With radio frequency, the wavelength or the frequency of radio communications is very low, so it's broad. So it kind of goes all over the place. With light, it's very directed, so you have to really point very precisely. Sort of, you know, if you're using a laser pointer and you're trying to hold it on one spot and your hand's kind of shaking and moves around a little bit, we have to point a lot more accurately than that.
Is that going to be as sort of an added challenge for laser communication from space? Because I imagine over great distances, even those subtle shifts in movement are more exaggerated, if you will.
Yeah, that's correct. It is. And what we do is we use an active tracking mechanism. So from the ground side, there's usually a broad beam that illuminates the space side. And the space side uses that beam to figure out where it is. And there's an active tracking such that they can stay aligned to each other.
What's the big advantage? Because I've heard through the grapevine and through my own research that it means I'll be able to download higher quality movies in the future. Is that really the main benefit for laser communication, that volume of data?
Yes, definitely. It's the volume of data. So with laser communications, you can transmit a lot more data. That's because it's at the higher frequencies, and so you have a lot more bandwidth. This is the reason why terrestrially we've replaced a lot of the long-haul copper with fiber optics with laser communications. It's the same exact reason. There's other advantages too, though, because it's so directed, it means we can put the energy exactly where we need it to go. And so that means the satellites, the apertures, the telescopes can be a lot smaller. And so when you're launching something like LCRD to GEO, it costs a lot to get something big, where if you can put it in a smaller package, it'll be a lot cheaper. So that's another big advantage. There's actually a third advantage, which is the RF spectrum is very contested, so you have to buy spectrum in order to transmit over the air. And optical communications, because it's so directed, you're not really like fighting with the other signals in the air. And so you don't have to worry about that. You can just go where you need to go.
That also means that weather might be a factor for laser communication, because obviously you're not competing for space, but you might have to compete with the elements.
You do, definitely. We are sensitive with laser communications to clouds, so when you're clouded out, you might not be able to get your signal. It also means that just going through clear sky atmospherics, we have to deal with what's known as atmospheric turbulence. The signal is going to increase or decrease in power, and it's going to do so over some time period, and you can't predict when you're going to get something loud or when you're going to get something quiet. And so you have to use coding or other techniques to still be able to transfer your data error-free instead of just losing bits and pieces of it as you try to go.
I imagine that's a pretty difficult and challenging thing to do, especially from space.
I certainly am impressed by the people who've come up with all the different codes and the techniques that allow us to do all this.
Now, do you have your own personal ground station where you can have them send data directly to your office there at MIT, or do you have to actually go to the official ground station?
I wish. We have been discussing and thinking about how to make low-cost optical ground station terminals, but I think we're a little far from having one that I can carry in my pocket.
Well, if you figure that out, let me know. I'd like to get in on the ground floor on that kind of opportunity.
So to speak.
Yeah. I like the way you guys think up there at MIT. That's awesome.
Thank you.
You can tell that Jade is having a fun time at Lincoln Labs working on the LCRD mission.
Absolutely. And the partnerships that, are always there with NASA missions, and in this case, between Lincoln Labs and Goddard, NASA has partnerships domestically, internationally, and those type of partnerships are showing up in bright colors here with LCRD.
What's even more important is that during that interview with Jade, we still haven't received the videos from Blair on his laser relay system.
Not one.
Now, see, guys, I'm a little disappointed because we're on a brilliant trajectory there, and then you had to bring this up. Now, I did some research. You have received everything. In fact, Franklin, your disk is full. So it's there. We're going to unpack that. But more importantly, not only was Jade a huge inspiration, but also it's not just about that technology. It's about the mission end to end. It's about ground stations. It's about going from space to the relay, down to the Earth and back. It's the whole picture. And to really understand this, we need to talk to Risha George. She's really involved in the ground station and the aspects of the mission that support just that, the successful completion of LCRD. Not only that, I'm sure when she looks at my schematics, she'll see that just like the ground stations, you guys have received the data you need. Let's hear from her first. Risha, I know you do a lot of work with ground stations at NASA Goddard. How does that relate with the laser communications relay demonstration?
I work on the Access project, which is it stands for, as we have many acronyms at NASA, and this is another one, Advanced Communications Capabilities for Exploration and Science Systems. And we're actually taking over operations of the LCRD after payload commissioning, approximately 2 months post-launch. And we are also responsible for one of the optical ground stations that's located in Hawaii as well. So we partnered with MIT Lincoln Laboratory to install an optical ground station there, which is one of 2 that will provide laser communication services for LCRD.
So once LCRD is commissioned and operational, tell me a little bit about the relay itself. Where's the signal going and how is this going to be demonstrated effectively?
So LCRD will be in a 2-year experiment phase, and there's certain objectives that they want to achieve during this time. We want to understand the optical link performance between LCRD and a user terminal. So there's a space-to-space optical link there to verify and validate and understand how well that works and improve performance where we can. Additionally, we want to understand with the relay function, there will be 2 optical ground stations. So depending on weather and whether there's a cloud coverage or not, and basically establishing line of sight, we'll have an opportunity to relay that signal to one of the 2 optical ground stations. Just in case, there's challenges with weather, there's also an RF radio frequency backup option as well to get data down to the ground. And so what we're demonstrating is the ability to understand those optical links, but also we're testing out extremely high data rates, 1.2 gigabits per second, which is one of the highest data rates that we'll be operating at today.
And so tell me a little bit about this space-to-space connection. You said a user terminal in space. Who's going to be communicating with LCRD?
So one of the opportunities and the users during the experiment phase will be the International Space Station. The International Space Station, there's a user terminal that another organization at Goddard is providing. It's called Illumity, and that will be integrated to the ISS, and that will be one of the first experiment opportunities that LCRD will be able to utilize and demonstrate. And it also provides a great capability for the space station today because for their science data throughput, right now they operate at 600 megabits per second, and so this will give them a much higher data rate.
We also shoot a lot of video up there on the ISS. You could test that throughput by sending some maybe 4K video down at high data rates. Would that be possible if this is successful?
Absolutely. It just takes a connection, between the Illumity Space Terminal and the ISS as well, which is currently in work. And we're actually going to demonstrate that type of capability on, the Artemis 2 mission. And one of the opportunities there is to transfer high definition video as well as file transfers, which we would not be able to do without having this capability.
I don't know about you guys, but I'm really excited to see the whole picture. And Risha did a great job of talking about this mission end to end, from the ISS all the way down to the ground and how the system's going to be tested. But I got to tell you, I'm a little kind of disappointed. Everything on my end says you've got the data I sent, and I just don't feel like you have the confidence in my system that I think it deserves. So I wanted to kind of walk you guys back to the beginning and talk about some fundamentals, kind of how laser communication actually works. Like if you think about lasers, they're light, right? It's light. When you blend those two things together and you kind of confuse that, then now I see I've got your attention. So
while he's talking about that, I'm gonna tell our viewing audience about how NASA Edge traveled to Northern Virginia, to Northrop Grumman to talk to NASA's Javier Ocasio-Perez about the final preps of LCRD in the clean room before it was shipped down to Florida.
And that's how this works. Javier, it is so great to be in the clean room here at Northrop Grumman with the spacecraft that is carrying the payload for LCRD. Can you give us an update on the mission?
Yes, so LCRD is currently attached to the STP-SAT-6 spacecraft. So a little bit of history. LCRD was put together back at NASA Goddard Space Flight Center, where we attached all of its pieces, the flight panel, the optical modules, the flight modems, and other software-related components. Over there at Goddard, it went through environmental testing, including thermal vacuum test, vibrations, acoustics, and all sorts of electrical and functional tests before it got delivered here to Northrop Grumman to be integrated to the spacecraft.
But of course, it doesn't end there. Now that it's here, you had to do even more work once you're here with the spacecraft.
Yes, that's correct. That was just a milestone, delivering the payload here to Northrop Grumman. Then we started a brand new, exciting chapter. We had to do standalone testing with our team to make sure LCRD survived the shipment from NASA Goddard to here. Then we got to the point where we're electrically integrated and then mechanically integrated, and then we became part of the full STP-SAT-6 spacecraft. Then we went through a range of space vehicle level environmental tests, including electrical magnetic resonance signaling, radio frequency compatibility tests, and additional thermal vacuum testing at the spacecraft level.
So Javier, what else is included on STP-SAT-6?
Great question. So LCRD is a hosted payload as part of the full STP-SAT-6 mission. As you can see in the overall spacecraft, at the very top, there's a box called the payload module, which includes payloads and instruments from other locations like the Air Force, universities. Then in the middle, you see the big plate or flight plate, which has LCRD. So LCRD is the biggest payload in STP-SAT-6. And then the rest of the components, the cylindrical shape and the boxes in the bottom, are part of the spacecraft of the observatory.
And so tell me a little bit about some of the challenges you've faced during this process.
Yes, so putting together LCRD for flight, it's been a challenging process. So keep in mind that we're demonstrating a technology that was developed by MIT Lincoln Labs. So they developed the technology, but it was not meant to be flown into space. So that's where LCRD came in, and we adapted the technology to fly it into space and make sure that it survives all the space environments. Some of the challenges, we had many, but I'll mention a security aspect. We had some boxes with data that's sensitive, so we had to convert our clean room back in NASA Goddard to be secure, and that involved shutting down access to windows, secure doors, and it took a lot of effort, but it was necessary for the type of work we were doing. Other challenges that we had is sometimes boxes have design flaws, and then you have to remove them from the payload. We had a particular situation with the optical modems back in 2019 where we had to remove them, repair them, and they have to go through a range of environmental tests again after reintegration. And then another one that's very recent is the whole COVID-19 pandemic. It hit us pretty much at the point after we were already delivered to the spacecraft vendor here in Northrop Grumman. So we had to adapt very quickly. We had to use masks, keep the distance. We had to modify how we did the control room operations. We had to keep desks empty in between just to protect our people, because obviously the people are the most important asset for putting together, LCRD and all the hardware.
And of course, you're going to be down at the launch, right? You still have work to do once you get down to Florida.
Yes, that's correct. So right now, we're still here at the spacecraft facility. We are in the phase of doing closeouts, which is basically making sure the spacecraft is ready for launch. We're removing pieces that don't need to be there for flight. We're putting finalization touches on the thermal blanketing to make sure the spacecraft's going to survive the environment in space. After that, we're going to pack and ship, get to the launch site, and then we're going to do additional testing to make sure that not just LCRD, but the entire spacecraft survived the trip from Virginia to Florida. And then at that point, we're going to get ready, we're going to get buttoned up, and then start counting for launch.
Well, keep up the good work, Javier. We look for very good things from LCRD and future tech demonstration missions in the future.
All right, thank you.
You know, guys, it's really cool to see Javier in the clean room, knowing that the spacecraft is healthy. It's down at the Cape now, getting ready for final preps for launch, and looking forward to just a great mission, a great launch, and seeing this technology demonstration actually work.
Yeah, it's going to be special. Javier was a real cool guy, and I was with Blair along for that trip, and he is genuinely excited about what the future holds for LCRD.
And this built on previous missions, like LLCD, which is a lunar laser communication demonstration, which was on LADI, I believe, years ago.
That's right.
But now this is sort of the next step.
Big steps.
Yes, that's right.
Yeah, and we want to remind people, be sure to tune in to launch coverage. Be sure to check the website. Make sure that you pay attention to this incredible historic launch. It's going to be a good time. And a lot of people are going to be really surprised and just overflowing with joy and excitement over this mission. And part of that enthusiasm, at least a little bit, they're going to have is about what I'm about to share with you guys. Now, listen, I got to be honest with you. You guys haven't exactly fallen in love with and embraced my own tech demo. I appreciate that. But I'm just going to show you real quickly that I was right the whole time and that my system worked flawlessly, and you guys are going to have to eat crow. All right? So just real simply, I know you don't believe me, but just minimize the call, Franklin, and you guys will see that all along my system worked absolutely flawlessly. Did you get it?
Whoa.
Terabits. Read it and weep, guys. Am I right?
Get out of here.
Genius.
This is not
absolute true. Genius. I am a genius. Thank you, Mike Rice. Thank you, Jade Wang. Thanks to all the people that made it possible for me to utilize my brain cells in a way that would help NASA and would actually demonstrate this great technology. I just want to thank everyone. And what else can I say? You're watching NASA Edge.
He did something. Yeah. Something is wrong with this. Terrible.
Gigabytes, terabytes, zettabytes.
What makes data visualization a bit different from other types of animation is that some component of the visual, some aspect of the visual is directly based on some type of science data. So in the case of the tour of asteroid Bennu, the OSIRIS-REx trajectory is actually based on mission data. The model itself, the asteroid model, that is real LiDAR data that was collected from the OSIRIS-REx spacecraft. The imagery that you're seeing wrapped to the surface of Bennu, that is actual satellite imagery taken by the spacecraft. And so that's kind of the difference between visualization and animation, is we're showing real data. This is the real asteroid. So if we zoom all the way in on a boulder, that's the real boulder. That's what it looked like from the perspective of the spacecraft. I'm Kel Elkins, and I was the lead data visualizer on the tour of asteroid Bennu.
I'm Dan Gallagher. I was the producer and writer on the tour of asteroid Bennu. Tour of asteroid Bennu was inspired by an earlier video that was also made by NASA's Scientific Visualization Studio, and that video was called Tour of the Moon. The visualizer, Ernie Wright, used elevation data and high-resolution imagery from a NASA spacecraft called the Lunar Reconnaissance Orbiter, and he was able to fly the camera very close to the lunar surface and show the actual textures, shadows, highlights, just the way that they would appear if you were hovering close to the surface of the moon.
So we kind of borrowed some of those techniques for the tour of asteroid Bennu, really using lighting as a way to help viewers understand the shape of Bennu and the shape of these different geological features we were zooming in on, which just it really helped the visualization come to life.
So a good example of how we use LiDAR comes about halfway through the video when we take viewers to a boulder called the gargoyle. Now the gargoyle has a very complex amorphous shape, and it looks really different when you see it from different angles in two-dimensional photographs. But when we finally got a good 3D model of gargoyle, Kel was able to put a virtual camera down near the surface of Bennu and rotate it around the boulder in a way that we never could with two-dimensional imagery.
So something really cool about working on this particular visualization, and actually all the visualizations we made for the OSIRIS-REx mission, was as the spacecraft got closer and closer to the asteroid on its way there, and as it spent more time studying the asteroid, the models got better and better. The data that was collected was getting better and better. So some of our early visualization tests, we had this relatively low poly model of the asteroid, and we could only push in so far with the camera. You can't push in too far because then you just see individual polygons. But as we got further and further along, we ended up with 5-centimeter resolution tiles that you could push all the way into individual boulders. And that's just the nature of how these science missions work. The more time you spend with something, the more data collect, the better the models get.
Missions like OSIRIS-REx take us to places that we haven't been before, literally new worlds that we've never experienced. But they show us those places in ways that can't always be easily seen. Tour of asteroid Bennu gives us a way not only to show the public what these places are like, but it almost gives us a remote presence. It allows viewers and even scientists on the mission to see these objects up close through technology.
NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening, everybody. Thank you for joining us tonight. My name is Mark Razzie from the Public Services Office at JPL, and again, want to thank you so much for joining us for this edition of the Von Karman series. Tonight, we're going to explore the infrared spectrum, or at least some of it. Now, William Herschel first discovered the infrared in 1800, but it wasn't until the mid-20th century that real research into that part of the spectrum began. But when it did, it began in earnest. There have been many instruments, telescopes, and spacecraft that have all worked to reveal mysteries hidden in the infrared, but there are still plenty of unanswered questions. Tonight, our guests, who are but two of very many people working on these projects, by the way, are going to talk about 2 upcoming missions that hope to deepen our understanding of our universe by continuing to delve into the infrared. Helping me out tonight with the Q&A is our co-host, JPL Public Outreach Specialist, is our Caitlin Soares. Hi, Caitlin.
Hello and welcome, everyone. As Mark mentioned, my name is Caitlin and I work in public outreach at JPL. We have a fascinating program for you tonight and we want you to be involved in the conversation. So please ask questions in the chat and we'll try to address as many of them as possible tonight throughout our discussion. If you don't see the chat for some reason, please refresh your browser and it should appear. And I'll turn it back over to Mark now so he can introduce our brilliant speakers for tonight's program.
Thank you very much, Caitlin. So our guests tonight are Dr. Dita Markovich, who is a research scientist at Yale, working on the Euclid mission, JP, and Dr. Phil Korngut, who is a research scientist at Caltech and the instrument scientist on the SphereX mission. And good evening, my friends. How are you guys?
All right.
Super happy to be here.
To be here.
Thanks. Our pleasure. So, Phil, to set the stage, would you be so kind to give us a little bit of a primer on the electromagnetic spectrum?
Sure, be happy to. All right. Well, when you think about fundamental measurements in astronomy, there's really one observable we're talking about, and that's electromagnetic radiation. Now, you're more familiar with that term by its colloquial term, light. And all the signals that we're measuring, from the gamma ray through X-ray and all the way to the radio, those are all just different flavors of light. And the parameter which governs that flavor is what we call wavelength. So what you're looking at here in this plot is the electromagnetic spectrum that is accessible to astronomers. That x-axis there in wavelength is a logarithmic scale, and it spans 15 orders of magnitude. So that's literally a factor of 1,000,000 times a billion in the available light that's out there. The way you think about those flavors in terms of your real world is in color, except it's far out from what balls are used. If you go to the next slide, you can see in context the opposite. Every peak light that you've ever seen in your life from red, which spans only about less than a factor of 2 wavelengths. So it's a pretty wild kind of in what to think about. There's 1,000,000 colors out there you could see just over there. So there's also a effects which there's all sorts of from object. It's not a surprise when eyeballs trade with if you can, we'll show the click on the next. So this very mission is my favorite here on Earth. The most kind of star here is star is on the order of 700 from peaks, and it looks like zoom in on the sun, which is green at 100 around right there. Right at and for eyeball, then that's a red day. So and there and all sorts of energies which are emitted there, only in not in the sun ray to even to them. The problem with doing that kind of observation our home. If you click, you can the next slide. So, great for things like breathing and living on. It's not so great for looking through. So, all of those magenta lines you're seeing there, that's absorption features in our Earth's atmosphere. So, while air looks clear to you in the optical, if you look in the near infrared, it's not really clear stuff. It's not forming. Not to mention that everything that you're on Earth that's everything room temperature is actually glowing in emitting. So it when you see light astronomy and up into space to get off.
So, and if you would be so kind, tell us why the spectra are so important in astronomy.
I guess what I should say, I'm happy to do that. Astronomy is kind of like this It's not going to be quite like other science where you can, put something in a lab and poke it and see what happens and then, figure out the laws of the things that we're interested in are really, really far away. So all we can do is kind of sit here and hope that information, on its own. And so things that we look at stars and if you're observing galaxies are much farther away. What we do is we sit here and we collect coming to us from a common way to us from reaches us is we're talking about the light, which what I'm talking about here. And light comes to us. So this light, huge collectors of light or telescopes to capture, and then of course we examine. We try to get all the information that's in this light, and what we do is we break it wavelengths that we do, these are energies, which is field has been. And these spectrum that they contain a specific, basically a lot of the chemical properties, the thermal properties, and the kinematic properties of the thing that's emitting that light. So the lights are the properties of the star, galaxies, source, and so we can have like very small ranges. We can have in wavelength or frequency where there's a bit of extra light in. Those are called emission. Or we can have part of the spectrum where there's a little bit less light. So if you show the next picture, you can see I've sort of made shows a kind of lines where there's a little bit less light, and there's an emission light with a little bit more light, and this is a specific pattern that we can understand really well because it. The pattern of the emission with these lights might appear in different, if you have different types of stuff that's emitting the light. The temperature, the light is a pattern. If there's some kind of something of the emitter of this light. So let me first tell you about the Doppler. About sound. Or effect you would if you have an emergency siren you and just be an emergency, and so the pitch of the siren higher than you. If the is higher, it's as if the sound waves get stretched out. Pitch falls. And it's really interesting. But the big difference is, one of the big differences is that the speed thing that is emitted has to be a lot higher. That emergency vehicle can be higher than of that kind of shifting effect to be observable. So what happens is if you have a distant galaxy that is for some mysterious reason moving away from it's as if wavelength stretch the red part of the spectrum, and if the galaxy was moving towards you, the blue shift, and you can measure this red light shift, blue shift. He tried so wormhole galaxy where he shifts. You look at this relation. They said, okay, if we measure redshift, get at this next shift. and so only what you're seeing damage. Hubble function.